or ask. Let us now, class 10, discuss about something very, very important for you all, which is the factors affecting the heat absorbed by a body. Now, if we denote the heat absorbed by a body by capital Q, then the heat absorbed by a body is dependent on three things. That is the mass of the body, the change in temperature meaning either the rise or fall in temperature, and it is also dependent on the nature or the material of the body. Now what we see is the heat absorbed capital Q by a body is directly proportional to the mass of the body. Now mathematically writing, we get Q is proportional to M. Now what this means is, let us discuss an example where we have, say, these two pieces, or let us say these are two pieces made up of copper. Now the weight of this is, or rather the mass of this is 1 kilogram and the mass of this is 10 grams. So obviously this has more mass. Now say the initial temperature of both of these two bodies, of course they are made up of the same material, copper, do not forget. So the initial temperature of both of these two bodies is, say for example, 10 degrees C. Now what we want to do is, we want to raise their temperature by the same amount. So to say, let us say initially they are at 10 degrees C, both of these two materials, and we want to raise the temperature to 15 degrees C. So we want to raise the temperature by 5 degrees, so to say. Therefore, in which case do you think to raise their temperature by the same amount, by 5 degrees, in which case do you think we need to give more heat? Obviously, we need to provide more heat in this case. To raise their temperature by the same degree, by the same amount, and although they are made up of the same material, we need to provide more heat to this body having more mass. Okay? And in order to raise the temperature of this body by the same amount, 5 degrees, we need to provide lesser amount of heat. So that is what it means, remember. The heat provided to a body or heat absorbed by a body is directly proportional to the mass of the body. More the mass of the body, we need to provide more heat. Lesser the mass of the body, lesser heat we need to provide. And of course, no mass, no heat. Therefore, Q and M are directly proportional. Likewise, the amount of heat that is to be given to a body or that is absorbed by a body is also dependent on the difference in temperature. Or so to say, now let us talk about these two pieces. They are of the same mass and they are made up of the same material. Let's say for example, again copper. And this case is they have the same mass. Say both of these two materials are of 500 grams, half a kilogram. Now I want to raise the temperature of this piece of copper having mass 500 grams of course on my right hand by 10 degrees. Say this is initially at 0 degrees C. Both of these two are initially at 0 degrees C. I want to raise its temperature to 10 degrees. So the change in temperature for this will be 10 degrees C. Whereas I want to raise its temperature by 100 degrees. Initially it is at 0 degrees C. I want to raise its temperature to 100 degrees C. They are of the same mass. They are of the same material. In this case, I want to raise its temperature by 100 degrees C. In this case, I want to raise its temperature by 10 degrees C. So in which case is the difference in temperature more? In the case of this body, of course. Alright, so therefore, since the difference in temperature or the rise in temperature is more in case of this piece of copper, so therefore we need to provide more heat to this body, of course. Okay, this has lesser temperature difference from 0 degrees C to 10 degrees C, therefore we need to provide lesser amount of heat compared to this, of course. So therefore we write Q is directly proportional to the difference or change or rise in temperature. More the rise in temperature, more the change in temperature we need to bring about, okay? So more heat we need to provide. Lesser change in temperature, lesser heat. No temperature, no rise in temperature, okay? We want to keep the temperature constant, obviously we do not need to provide any heat. So therefore these two things are, that is the amount of heat provided to the body and the difference in temperature, they are directly proportional. Furthermore, the amount of heat absorbed Q by a body is also dependent on the nature or material of the body. Like for example, this is a good conductor, this is some metal, again say copper, and this is a bad conductor. Alright, say this is water. Okay, now they are of the same mass again. Say we have 1 kilogram of water and 1 kilogram of copper. Okay, and we want to raise the temperature by the same amount. They are initially at 10 degrees C. Both of these two things are initially at 10 degrees C. They have the same mass, and we want to raise their temperature by the same amount, say to 20 degrees C. So the difference in temperature in both the cases, in case of both the bodies, is 10 degrees. They are of the same mass. We want to raise the temperature by the same degree, but they are different material. Okay, so do we need to provide the same amount of heat? The answer is of course no. Okay, since they are different material, one is a good conductor of heat, the other is a bad conductor of heat. So in case of the bad conductor of heat, we obviously need to provide more heat to raise their temperature by the same amount. In case of the bad conductor, we need to provide more heat. In case of the good conductor, we need lesser amount of heat. We need to provide lesser amount of heat. Therefore, the amount of heat absorbed or that is provided to a body to raise its temperature by the same amount is also dependent on the nature or material of the body. So these are three important factors, remember that. Now, from relation number 1 and relation number 2, we can combine both of these two relations, and what we can write is, we can write Q is proportional to M delta T. So combining relation 1 and relation 2, we get a third relation, which is Q is proportional to M delta T. Now, a proportionality sign can always be replaced by an equal to sign, provided we add some constant, and therefore we get Q is equal to MC delta T, where C is the constant of proportionality that we are adding here. Now, this is a very, very important constant for you all, remember. This C has a name. This C is called, SP means specific, okay, you have to write specific in full. So specific heat capacity. It's called specific heat capacity, a very, very important constant for you. And you know, this equation in itself is very important for you. Q is equal to MC delta T. The amount of heat absorbed is equal to the mass of the body times the specific capacity of the body times the change in temperature. Okay, now let's talk about this specific heat capacity. Now, any material, okay, any material will have its specific value of specific heat capacity, or so to say, will have its own value of specific heat capacity. Like copper will have its own value of specific heat capacity, water will have its own value of specific heat capacity, iron will have its own value, aluminium will have its own value. Okay, so different substances will have their own characteristic value of specific heat capacity. So this quantity over here, specific heat capacity, is a characteristic property of a particular material. Every material will have its value of specific heat capacity, remember. Alright, now if we are to define specific heat capacity, let me erase this heading over here. You don't need to memorize the definitions, remember. From this equation itself, we can write C is equal to Q by M delta T. This is what we can write. Now, if M is equal to unity and delta T, the difference in temperature is also unity. Now, if you are working in SI system of units, then M is unity, means M is 1 kilogram and the change in temperature is 1 Kelvin or 1 degree C. So therefore, if M is unity and delta T is unity, what happens? We get then C is equal to what happens? Q. So therefore, how do we define specific heat capacity? Specific heat capacity is equal to, or is the amount of heat absorbed by a body, or it is the amount of heat that is needed to be given to a body having unit mass to raise its temperature by unit degree. Alright, so this is how you can define specific heat capacity, remember. You can say specific heat capacity is the amount of heat that is given to a body having unit mass to raise its temperature by unit degree. Okay, so from the mathematics, from the equation itself, you can write the definition. Okay, so you can rewind the video, listen to the definition of specific capacity again, and write the definition yourself. I repeat one more time. Specific capacity, as you can see, is the amount of heat that is given to a body having unit mass to raise its temperature by unit degree. Remember that. So that is a specific heat capacity. And talking about the unit for specific heat capacity, since it's a physical quantity, it will have its unit. So let me erase this. I hope you've already copied this. So let me erase this stuff. So you can see specific capacity, this is small c by the way, is Q by m delta T. So talking about its unit of small c, that is specific capacity, is, you can see its heat is measured in joule in SI. I'm talking about SI, okay? So joule divided by kilogram divided by Kelvin. So you can write joule per kilogram per Kelvin. This is the SI unit, remember. This can also be written as, or the other unit will be joule per kilogram per degree C. So this is another unit for specific heat capacity. You can write other units also, like heat is also measured in calorie, so calorie per gram per degree C. So this is calorie per gram per degree C. So this is another unit of specific heat capacity, remember. Alright, now we need to talk about one more term or one more quantity, and that quantity is from this very equation itself, or from this very equation itself. The quantity that we are going to discuss, let me first tell you about that. It's called thermal capacity. It's called thermal capacity, or also called heat capacity. It's called thermal capacity or heat capacity. Okay, so what is thermal capacity? It is, by the way, denoted by a capital C. So capital C, remember, is mass times the specific heat capacity. So to say, this is the relation between heat capacity or thermal capacity and specific heat capacity. So from this equation, m into c will be how much? Q by delta T. So this becomes Q by delta T. So this is your heat capacity, remember. And how do you define it? The definition again is very simple. So you can see the heat capacity is Q by delta T. So from here we can write, if delta T is unity, then heat capacity is the quantity of heat that is given to our body to raise its temperature by unit degree. Okay, so that is your heat capacity. Let me erase this. So let me write the definition for heat capacity. You write the definition of specific heat capacity yourself. It is the amount of heat required to be given to a body. Let me write that. Required to be given to a body to raise its temperature by unit degree. So this is how you define heat capacity. Whereas specific capacity is the amount of heat required to be given to a body having unit mass to raise its temperature by unit degree. That is your specific heat capacity, remember. Okay, likewise now what we need to do is we need to find the unit for heat capacity. So it will be joule per Kelvin, or joule per degree C also you can write, or the other unit you can write is calorie per degree or calorie per Kelvin. Alright, so that would be the unit for heat capacity, remember. So unit will be, let me write over here, joule per degree C or joule per Kelvin will also do. The other unit could be calorie per degree C. So you can write this much. So this is the unit for thermal capacity or heat capacity, remember. Now sometimes what is done is, you are asked a question where you need to give the difference between heat capacity and specific heat capacity. Now I must have told you, whenever you're writing differences between two things, if you know their definitions, start with their definitions. So you start with the definition of heat capacity and specific heat capacity. The second thing you write is, specific heat capacity is not dependent on the mass of the body, remember, whereas heat capacity is dependent on the mass of the body. Like for example, I have this small piece of copper, I have this bigger piece of copper, okay, if they are cut out of the same very big piece of copper, okay, and one is this big, the other is this big, so both are copper, remember, irrespective of their masses, they will have the same value of specific heat capacity. This is specific to a substance, therefore the name specific heat capacity. Whereas these two pieces of copper, since they have different masses, they will have different values of thermal capacity, because thermal capacity is the amount of heat that is to be given to a body to raise its temperature by unit degree. So I have these two bodies, okay. So in this case, to raise its temperature by a unit degree, I have to provide more heat. Why? Because it has more mass. Whereas this has lesser mass, therefore to raise its temperature by a unit degree, I need to provide lesser amount of heat compared to this. Okay, whereas their specific heat capacity will be the same. Alright, so that will be the second difference between heat capacity and specific heat capacity. Specific heat capacity is independent of the mass, heat capacity is dependent on the mass, and if you want to write third difference also, you can say, you can talk about their units. The unit for heat capacity is joule per Kelvin or joule per degree C. You can write the unit for specific heat capacity is joule per kilogram per Kelvin or joule per kilogram per degree C. So this is about very, very important, topic, that is specific heat capacity and heat capacity. Thank you.